All right, let's find and classify the equilibrium points of the following system. X prime equals y, y prime equals minus sine of x. And you'll see at the end, there'll be a really cool physical significance to this. So first off, let's find the equilibrium points. Equilibrium points, which I like to remind you, you just said x prime equals 0 and y prime equals 0 because they don't move. And so what we have, y is 0 and minus sine of x equals 0. And so in particular, this gives us sine of x equals 0 and y equals 0. And I like to remind you, the zeros of sine are yours truly. So x is Peyam and y equals 0. So in other words, the equilibrium points are simply Peyam 0, where m is any integer. All right, and now let's do the classification. So it's the yassification of the equilibrium points. Step 2. Classification. Which, remember what we need to do, we need to find the derivative and plug in the equilibrium points. So let's do the gradient of f at xy. So remember, you differentiate the hell out of everything. So dy over dx, dy over dy, d minus sine of x over dx, and d minus sine of x over dy, which then becomes 0, 1 here. So then that becomes gradient of f at xy. So I believe 0, 1 minus cosine of x, 0. And now we need to plug in x equals Peyam and y equals 0. So now the gradient of f at Peyam, 0. So in this case, it becomes 0, 1 minus cosine of Peyam and 0. Now we can simplify this. So cosine of pi is 1. So yeah, cosine of 0 is 1. Cosine of pi is minus 1. Cosine of 2 pi is 1. Cosine of 3 pi is minus 1. So notice we alternate between 1 minus 1, 1 minus 1. So in fact, cosine of Peyam, it's minus 1 to the m and 0. Okay. And so this is our matrix A. And now let's find the eigenvalues of this. So determinant of A minus lambda I. That's determinant of minus lambda 1 minus 1 to the m. There's a reason why I leave it like that. Then minus 1. And then if you do the determinant, this gives you minus lambda squared minus, so careful, minus 1 to the m. I know it's a lot, and that becomes lambda squared plus minus 1 to the m. And you want to set this equal to 0. And now notice there is different behavior depending on whether m is even or odd. Because if m is even, this is 1. If m is odd, it's minus 1. And so it makes sense to split it into cases. So let's do m even. I can't even. But then in that case, minus 1 to the m. Think like minus 1 squared is 1. And then we get lambda squared plus 1 equals 0. And that gives you lambda is plus minus 1. And in this case, the real part is 0. So this is purely imaginary. So if you remember the recipe, in this case, we call the equilibrium point. It's neither stable. So either degenerate or neither stable, unstable or saddle. Just as an aside, we will see why that's so cool. Technically, if it's purely imaginary, we call it a center. So aside, this is called, again, don't worry about this. So this is called a center. A center. And that's because the solutions are circles or ellipses. Are circles or ellipses. And again, this will be cool in terms of application. So if you want to draw the face portrait, it just spins you right round, right round. Not quite a circle, but yeah. That's sort of what the face portraits look like. So if you find something purely imaginary, technically, it is a center. So that was the first case. The other case, if m is odd, and odd, and then in this case, minus 1 to the m, that's minus 1. So think like minus 1 cubed. And what we get is lambda squared. Minus 1 equals 0. And so we get lambda is plus minus 1. And since it's mixed sign, this is called a saddle. So in this case, Peyam 0 is a saddle. So in other words, what is our answer? So our equilibrium point Peyam 0 is, so it's a center if m is even, and a saddle if m is odd. So it's kind of cool. The equilibrium points, they all alternate between centers and saddles. So let me draw this with a cute picture. Okay, I need this in red. So again, whenever it's even, so think 0, 2 pi, 4 pi, it's a center, like this. But when it's odd, like pi, 3 pi, like this, the equilibrium points are a saddle. So this is center. And this is saddle. Okay, you don't need to draw the equilibrium points. This is just for cultural reasons. Why? So once again, the equilibrium points, they alternate between center and saddle. And now I can give you the cool application because it turns out this system is nothing other than the pendulum equations. This is the ODE of a pendulum, which really alternates between two states. It goes up and then down and then up, down, up, down. And this is illustrated by the equilibrium points. In fact, I want to show you a really cool picture of this. So here, once again, we have the sort of face portrait of a pendulum, and you can see that we really alternate between saddles and centers, because at the red points, the solution sort of are circles, but at the green points, they become saddles. So it's kind of cool how nature works out like that.